Welcome back. This is the IEDM 2020 short course on memory for secure computing part 2. Now let's take a look at techniques to secure memory. Probably the oldest technique is called the no execute stack. And this really harkens back to that buffer overflow attack that we saw early on in the previous section. By overwriting return address, you can execute code that's on the stack. So what system developers did is they allowed you to turn off the execute capability in the stack. And that's called the no execute stack. And it helps. It helps. But, there's many ways to get around this. There's ways to execute code in the heap. There's ways to execute code using only the code segment by reusing existing code called return-oriented programming. So there's a variety of techniques, but it certainly makes the system harder to penetrate when you can't execute on the stack. Most systems today prevent this by default. Another really interesting approach, which is widely deployed, even in embedded systems, anything that has virtual memory can do this fairly straightforward, in this fairly straightforward manner, is address space layout randomization. The idea here is, remember when I overwrote that return address, I want to jump back to my code. Well, what if I don't know where my code is? What do I overwrite the return address with? And so the idea behind address space layout randomization is we're going to put all the code and the data in random locations. So when a program loads, it's going to randomize the location of the stack, the location of the heap, location of the global variables. And when it does that, then finding that information is going to be very difficult. It's going to be difficult to overwrite stacks. It's going to be difficult to know where to jump to. Now, moving the code, that's a little tougher, right? If you remember from assembly language, to move the code, we've got to be position independent. So, with old 32-bit x86, that was pretty tough to do because there was no PC relative jumps. But in today's systems, in x86 64 and ARM, RISC-V, we've now got really good access to PC relative jumps, PC relative loads. And so now it's fairly easy to build text that's completely relocatable. And so you'll even see the text get moved in modern ASLR systems. This is a really important technology. And of course, there's a variety of attacks that do what they call de-randomization, figure out where stuff is located. So, the popularity of this protection has led to so many attacks. Another really popular technique, and this is available, for example, OpenBSD has this on by default, is what are called stack canaries. A stack canary is, again, if you look at the buffer overflow attack, when you overwrite your local frame to get to the return address, what stack canary does is it inserts a random value in between the local variables and the return address. Now that random value is picked when the program starts executing. And it's just typically the same value for the whole program execution, but every time you run the program, it's a different value. And so when you overwrite the stack, you have to guess what that value is because the function won't return if that value doesn't match the secret key. Well, the secret key ain't so secret. It's in memory. So if you know where to find it, you can overwrite the correct value. This is a buffer overwrite attack. There's also something called a buffer overread attack. With a buffer overread, you're just dumping out memory to a network socket or something. And then it's possible to figure out what canaries are, just dump out the stack. If you remember the Heartbleed attack from a few years ago that was done to the bind server, that one of the reasons why that was so important to fix was because it was a buffer overread attack. So by when you have a buffer overread, you can leak all kinds of important secrets that disable things like canaries. Because if I can see what the canary is, I know exactly the value to overwrite, and then I can take over your return address. You can go even further with randomization. You can actually encrypt the pointers with a random value. This is called point guard. This is a technology. It was a commercial technology deployed in GCC. And what it did was when you would call a function, it would write a return address on the stack that was encrypted, sort of encrypted with XORing it with a key, XORing it with a key in such a way that you had to know that key in order to put the correct value on the stack. So if you were overwriting values on the stack, you needed to encrypt them in order to put them on the stack. Otherwise, when they XORed it with a key, you'd get just some random garbage and you'd jump to nowhere. Well, that's pretty nice. That's a pretty good technique, because now it's really hard for me to get in there and manipulate your memory, your pointers in memory, without that key. One of the challenges is that if I can dump out that value and I know what that thing points to, I can just XOR that known address against that encrypted pointer and I get the key. So XOR is a really weak form of encryption. Do not use it. DDR3 used it, for example. I mean, I just shake my head that people want to use XOR for encryption. It is easy to break. You don't even need to be a cryptographer. You just got to be clever. You want to go with strong encryption when you're going to apply encryption. And XOR is not strong encryption. It's weak encryption. And so it's really easy to break these systems. People are very clever in doing that. Sandboxing is it's a powerful memory containment technique. The basic idea is to use the virtual memory system to really partition your address space, to the finest granularity. And Chrome the Chrome browser especially uses this to really effectively stop a lot of attacks. The idea is, okay, people are going to try and attack my machine. I'm going to contain it to this one process, and you can't get to any of these other processes. So in Chrome browser, every tab is a different process. And within that process, the programs that run are very constrained. All they can do is make requests to these policy engines that allow it to access these HTML5 resources and a few other things that the browser allows you to access. Render stuff to the screen in a highly controlled manner. It's basically all the output of code that's JavaScript or other stuff that comes from the web runs in these sandboxes. And they have to go through these very, sort of strict policy engines in order to render to the screen or interact with resources on the system. And so if somebody hacks into one of these things, then, they still can only do what's allowed over this particular channel. They can't get out of these boxes because they're stuck inside these virtual memory address spaces. It's a pretty good idea. And the basic idea is people are going to hack these systems. So just, limit the attacks to these small boxes and then don't allow these boxes to do things. They can make any request they want. They're not allowed to do things that are damaging to the system. What's really interesting about what runs in the box is they use this what's called native client, native execution. And it's this really constrained form of code where they limit what can be in registers. They limit where entry points can be in the code. And as a result, they can do a lot of analysis of the code, and they can make some very strong guarantees about what the code can and cannot do. For example, in the native client execution, they can do reachability analysis on the code, and they can figure what are all the possible code sequences that could be generated using clever attacks, and do any of those possible code sequences do any illegal activities. And it's just a really powerful system to limit things like jumping in the middle of an instruction to create a new instruction. All this fancy stuff that that a hacker will do any day of the week. They can't do it in this system. It's a really powerful system. It's well regarded because it's really hard to attack. And then let's take a look at some row hammer protections. I think these are particularly interested to the semiconductor industry because we got to figure out how to stop row hammer. Remember, row hammer is this idea where I'm going to hit one line repeatedly and stop it. And there's a variety of techniques to stop row hammer. This is some work that I did with my graduate students a few years ago, Zelalem Aweki. And Zelalem basically came up with this idea of analyzing the miss stream out of the processor into the memory system using standard performance counters on the system. So this was a Linux kernel level analysis that was being done in this Anvil module in the Linux kernel. And it was basically looking at the performance counters to find out when is there a miss out of the L2 cache into the DRAM. And then when there was a miss, was that miss going to, was it hitting a piece of memory frequently? So he was keeping like a top end lines that have been touched in the last refresh cycle. And when the top number of lines, when the most access line got over a certain threshold, then it says, maybe we're going to be hammering here. And so then what he would do is he would initiate a refresh prematurely. Now, how do you do a refresh on a potential victim line? You just read it. Reading DRAM refreshes the line. So it's really easy to initiate a refresh. And it didn't cause much slowdown at all because these performance counters can measure these things very easily. It was really a very effective technique. Another effective technique that I've seen used that's a very effective is called the para technique, where basically what you do is with some small probability, when a DRAM row is accessed, you just refresh it at that time with a very small probability. And when you row hammer, that's a pretty effective technique because when you row hammer, you've got to hit that line frequently, right? So you're accumulating those small probabilities on that one line. And eventually that line's going to get refreshed if you keep hitting it. So to get around this, there's a variety of attacks. People are trying to figure out how can I more efficiently row hammer with less numbers of references? Can I hide those references, et cetera? So it's the arms race is alive and well in the row hammer world. Let's take a look at TPMs, trusted platform managers. You'll find these in a lot of systems, desktop, server system, even some embedded systems. And what the trusted platform module provides is a pretty nice capability. It's got a lot of the things you need to do efficiently in hardware. These are just small embedded systems that are embedded into bigger CPUs and bigger systems, okay? And they got a couple things in there. They got a good random number generator. You're going to need that because you got to come up with keys that are hard to guess. So you want a true random number source, something, electrical in nature, producing your random noise information. They have hash functions. They have asymmetric key and symmetric key computation capabilities, very powerful. They also have this other capability where they have what's called a non-volatile storage that's only writable by signed data. That's quite interesting. Inside them, usually burned right in the silicon, is the public key of the entity that can update that signed storage. And so you'll remember we have this notion of a hash, right? You can take a hash of a value, creates a hash value, and then you can encrypt that hash with the private key of that matches this public key. Then you can hand to the TPM that piece of information. The TPM will then decrypt that with the public key and then check the hash. If the hash matches the data, then it knows, oh, this was prepared by whoever owns me. I will now write it into the signed storage. So what can you do with signed storage? Well, the most important thing you do with signed storage is trusted boot. What is trusted boot? Trusted boot is getting into memory authenticated code and only authenticated code. That means that the BIOS is trusted, the bootloader is trusted, and the kernel is trusted, and the applications coming in from the kernel are trusted. So how do you do that? Well, what you do is you write the hashes of all these components into the TPM trusted storage. And before you put the component in memory and jump to it and start executing it, you take a hash of that value. You compare it to the hash in your trusted storage. If they're the same, what do you know? Well, you know that that code was prepared by the entity that is associated with my public key that's stored in my immutable register. And so I can trust that code. And now I can boot that. So, you know, Windows 10 has this now, iPhone has this. You know, it's really important to be able to attest, as it's called, through digital signatures, all the code that comes into the system before you execute it. That is incredibly powerful. Does it mean you're going to be free from, you know, people messing with this? No, not at all. You've heard of jailbreaking. What is jailbreaking? Jailbreaking is when you boot your iPhone through all of these checks. You come up into the kernel, and then somebody finds a bug in the kernel, and then we rewrite all of memory. So with our own operating system that doesn't have all these, you know, onerous features in it, like, you know, I have to pay to load these applications, or I have to pay to use the hotspot feature. You know, I can, with my hacked kernel, I can do all these things. So jailbreaking is basically redoing this entire process once a bug has been located in the kernel that can allow you to rewrite all of memory. And then that's an arms race too. Apple has got so much IP on how to lock down the memory structure once they've come out of boot in the kernel. And it's really impressive the amount of capabilities they have in their SoCs today. You know, moving beyond trusted platform modules and their ability to allow us to do trusted boot, we can start to look at things like trusted execution environments. This is like ARM Trust Zone or Intel SGX. What these capabilities allow us to do is, for the first time, a very interesting capability, the ability to run an application with what's called minimal trust. So inside my trusted execution environment, and that environment is called the enclave, I'm running code and data, and that code and data has some very special properties that is endowed into it by the trusted execution environment. And let me tell you what those are. The first one is, we don't trust any of this stuff over here. We don't trust the operating system. We don't trust the device drivers. We don't trust the boot code. We don't trust the application code, any other application code. We don't trust anything in this stack. What does that mean? That means we don't want, under any circumstance, for any of these guys to be able to look inside of us. Not even the operating system. You know, normally the operating system can do whatever it wants, right? It controls memory. But with an enclave, the operating system can't look inside and see what code and data is running inside the enclave. It cannot, unless it finds a vulnerability. So how do you do this? Well, you basically need very powerful memory barriers. They usually come in the form of sort of low-level protection mechanisms. So I can define part of my memory as inaccessible by any other application than the enclave application. That would be, for example, how ARM Trust Zone works. Intel SGX goes a little bit further. It says, if anything comes out of here into the DRAM or the swap, it's encrypted. It's authenticated. That means I've got, you know, hashes, encryption, etc. And the keys to get access to that data, again, are located in the enclave. And nobody can look into the enclave because of all those checks that, you know, non-enclave code cannot touch the memory of enclave code. Very powerful. Another feature that you find in these trusted execution environments is the notion of attestation of code. So that code can be signed with the public key of the developer, and only that code is allowed to be loaded into the enclave. And through the use of authentication, asymmetric key authentication, and hashing and digest, I'm able to ensure that code that is coming into the enclave is the code that is developed by a particular developer. So it's really powerful. Now, does this mean the security problems are solved? No. There are side channels galore on these systems because they look like they're a separate walled off part of the system, but in reality, they're sharing the same cache, they're sharing the same registers, they're sharing the same virtual memory, tables and stuff. It's hard to create really durable isolation. And for example, Intel SGX and ARM Trustone have both, people have found ways to sort of jump over that barrier and look inside the enclaves. But as a matter of technology, the barrier is high. It's hard. It's hard to get in there, but people have. And then also, there's code inside there, so you can just hack the code too if you want. I mean, if there's vulnerabilities in the enclave code, it's attested, so I know that it just because code is attested doesn't mean it doesn't have vulnerabilities in it. It's from this particular developer, but it could be buggy as all get out. So you still got to be wary of the fact that it's important to be able to realize that it's not the end of the security, but it's certainly higher levels of security. And I want to talk about technology. Maybe you've heard about this before. I'm a huge fan. It's called homomorphic encryption. And they always say homomorphic encryption is the holy grail of cryptography. And the reason why is because, cryptographers, they say, I want to secure your computation, right? So they think about, how do I secure your storage, right? When you're storing your data, how do I secure it? Use cryptography. When you're transmitting it from place to place, how do you secure it? So one's in storage, one's in flight, when it's moving around. Well, we can use things like TLS that we talked about earlier, where we can set up secure channels and communicate data through it. The Holy Grail has really been, how do I secure your computation? So when you're computing on data, it has to be decrypted. How do I protect that? Somebody hacks into your program, it's gone. What homomorphic encryption does is it leverages what are called homomorphisms on the ciphertext. Cryptographers have actually figured out how to perform computation on the ciphertext without a key. They can take encrypted integers, add them together, subtract them, and multiply them. It's really amazing technology. And so you can provide a computational service. This user can take this value, let's say it's their voice, Siri, what time is it, And they can say, encrypt that voice, send it up to the server, apply a function to that encrypted value, be it, natural language processing machine learning model, be it computer vision algorithm, whatever, and you get an encrypted result. So you've applied your algorithm to this data, and the result you got is encrypted. You didn't have a key. There's no plain text. It's really quite an amazing thing. And then you send it back to this user, and then they can decrypt it with the original key and see the actual result that you computed. Oh, it's 2:30 in the afternoon. I see that. What is so amazing about this is it eliminates trust in software. If somebody hacks the software, all they can steal is your ciphertext. They don't get your data. They just get your ciphertext. And it eliminates trust in hardware. If somebody backdoors the hardware and sends that data out the back, to, whatever nation state installed that backdoor Trojan, all they get is ciphertext because the algorithm operates on ciphertext. There is no plain text anywhere in the system. Really incredible. It's an exciting technology, but it's got some drawbacks. The two main drawbacks are it's tens of thousands to hundreds of thousands of times slower. And depending on the computation, you can even start dipping into the millions of times slower. It's just very expensive to do homomorphisms on ciphertext. Addition isn't so bad, subtraction isn't so bad, multiplication is a big mess. And then the other problem is you only get add, subtract, and multiply. So imagine writing a program and you only get add, subtract, and multiply. How do you do a less than to sort something? Well, try writing a less than with only an add, subtract, and a multiply. You got to do like a Taylor series expansion of the function that is less than. I mean, it's really complicated to program this system. Now, fortunately, machine learning is pretty relatively straightforward to map onto this framework. Nonlinear activation functions get a little bit funky, but there's a lot of research to try to solve that with just linear functions, piecewise linear functions. So there's a lot of value here, a lot of value. And the fact that you don't have to trust is really, really exciting. So this is something to watch. It's also an interesting area to look at from a hardware perspective. So that's some text that can help us protect our memory. Let's take a look now at future protections, things that are coming down the pipe in the research domain. These are things there's a bunch of stuff, but I'm just picking some stuff from my work that DARPA's put a lot of work into, SRC's put a lot of work into, the labs at Intel and AMD put work into. So these are things that you'll probably be seeing hitting the market here one day. The first is this idea of safe pointers. So if you want to protect memory, people generally agree that the road to protecting memory most effectively is to protect pointers. Pointers in languages like C and C++ are dangerous. They're very dangerous. They're dangerous because they don't include all the information that's necessary to ensure that programmers don't make mistakes and access memory that are not supposed to. And so what SafePointers do, and I'm specifically dipping from a project called the Cherry Project out of Cambridge, which builds into hardware these idea of safe pointers, is they put what's called a fat pointer in the system. So instead of just a pointer being a 64-bit location in memory, it's a 64-bit location in memory combined with the base of the object that it points to, the size of the object it points to, the permissions of what it points to, perhaps some temporal information about that object, is it still alive or not? And it packs all that into 256 bits, and that becomes the new pointer. Now, of course, that's less efficient than 64-bit pointers. Now your pointer's 4 times as big. Your program's going to have to do more work to deal with pointers. But in exchange for that, you get this very powerful capability where programs can't go off the end of arrays. They cannot go before the start of variables. They cannot randomly jump to a piece of code that is not their own. Really powerful capability. And it stops a lot of attacks. There's some challenges here. In particular, it can break legacy codes. But, it's a really powerful technology. Microsoft has invested a lot in evaluating this particular technology. Now, they said in a recent report that it only stopped about a third of the attacks that they've had to deal with in Windows, but that's a third of the attacks. There's a lot of attacks that could stop. And if it could be done efficiently, and if it's done hardware, it can be very efficient. This is a really interesting technology to watch. I know ARM is spending some resources looking at integrating into experimental platforms. This technology is a big European project to do that. DARPA spent quite a bit of resources evaluating this technology in the context of RISC-V processors. So it's a really cool tech and one to keep an eye on. In order to eliminate those side channels through caches, we're starting to see what are called randomized caches. These are really interesting technologies where you remember your traditional cache design, you've got a tag, an index into the cache, and then an offset into a block. And use the tag to figure out which way you match in, use the index to figure out which set to access, and use the offset to figure out which byte in the block that you're accessing. Well, what you do is you take the tag and the index, you put it through a cryptographic function, and then that maps you to a random location in the cache. It's consistently random. So once you go and access that storage again, you go to the same spot. But it'll basically make the mapping of a block to its location in a cache a cryptographically hard function. Now, remember that earlier attack that I talked about where I'm loading my cache with 2 lines, calling a piece of code and seeing which line gets knocked out. Well, now figuring out where to load my cache is a cryptographically hard problem. That's a very powerful way to stop these cache side channels. It's not completely able to stop them all, but it really raises the bar and makes it really, really hard to figure out what you're seeing from the other application. And then this is scatter cache, some work that came out of Europe that just applies a really powerful crypto function between the address and the way the data is mapped into the cache. There's some additional work. There was some work out of Georgia Tech called Caesar cache, where what Caesar could do is it could actually change the key to the cryptographic function while the cache was live. So that not only is this mapping into the cache cryptographically hard to figure out, but it's changing over time. So if I'm clever and posing experiments, like load this line, now touch this one, load this line, now touch this one, load this line, touch, oh, you knocked it out. I've found a connection, right? By rekeying on a regular basis, you've now made it very difficult to even do that. I mean, really impressive stuff. So this is one to keep an eye on, randomized caches. And I want to show you a little bit of my work too. This is actually an area that I've been quite involved in for the past 15 years, looking at how to build systems that are harder to attack from a memory perspective, as well as from a compute perspective. And so let's take a look. A project I've been doing with DARPA for the last 4 years is called the Morpheus project. The idea behind Morpheus, I'll show you this video and then I'll talk a little bit more about it. These are my students I worked with that were involved in the development of this particular technology. But let me play you this video. This is a video they made for an ASPOS paper we had. ASPOS likes everybody to make videos. And it kind of explains the idea behind Morpheus. And Morpheus, what Morpheus does, I'll just say short story, Morpheus really grabs onto randomization in a way that's quite powerful. So take a look at this.
In a world where software vulnerabilities are rampant and unsafe languages like C are exceedingly common, attackers are gaining more power by the second. To synthesize an exploit, attackers need access to an asset, such as pointer values. Defenses randomize these values to make it harder for attackers. However, hackers have found help around these measures.
Randomization.
But there's hope. Because there's Morpheus. To stop attackers from de-randomizing assets, Morpheus changes it from under them in a process called churn. Morpheus is a secure architecture targeted at stopping advanced control flow attacks, such as ROP. We leverage hardware in RISC-V to provide 2 layers of defenses, displacing memory into a superimposed address space, and encrypting code and pointers. These defenses, combined with churn, significantly hinder exploits. With hardware support, Morpheus can churn sensitive assets every 50 milliseconds with less than 1% slowdowns. With information changing so quickly, attackers are left with a system that is extremely difficult to penetrate and must resort to advanced probing. Because of churn, this challenge becomes a race against a short clock, a race that is nearly impossible to win.
Yeah, so that is very difficult system to penetrate. In essence, what's
Find out
happening.
more about Morpheus at our.
Let me go to the next slide here. Hello. There we go. We worked with DARPA to develop this in the context of, as you know, as Mark said in the video, in the context of RISC-V. So we took a RISC-V rocket core and we deployed this technology. And I want to show you what it looks like in the pipeline. We do two things in this particular implementation. We encrypt code and we encrypt pointers. Now, what does it mean to encrypt? We actually use strong encryption. We don't use XORs because people can punch through XOR encryption pretty easily. We use a cipher called Simon, which, if you've been involved in hardware, in the hardware implementation of strong ciphers, you'll know Simon is particularly nice to implement because it's just ands and ors and rotates. Half of the computation is just moving wires around. It's really impressive. And in a few cycles, you can have a fairly strong cipher. So in the Morpheus architecture, our goal is really to encrypt all the code. Now, why do you want to encrypt the code? You want to encrypt the code so that people can't figure out where the juicy bits are to jump to. They have this, when they try to reuse or inject code, both those become hard if the code is encrypted, because that key is a key that was selected when the program booted, and you saw this notion of churn. That key changes over time. So knowing what that key is that's cryptographically a hard problem. If you want to inject code, you got to inject the encrypted code because it's going to decrypt it whether or not you want to. If you want to reuse code, you got to figure out where the interesting bits are in the encrypted code. Really, really hard to do with strong encryption. Possible, but hard. It's really hard. And then we encrypt code pointers as well. And when you encrypt a pointer, forging the pointer becomes very hard because, again, they're changing their keys on a regular basis. So if you want to jump to a particular piece of code, you got to figure out, how do I create that encrypted pointer? You could look at other encrypted pointers in the system, but that's really difficult too because they're changing their pointer values on a regular basis. And so you end up making the system that's really, really hard to manipulate pointers and to figure out what the code's doing. And when you do that, you can stop very effectively a class of attacks called, code injection, control flow attacks, runtime code execution attacks, things that are the most dreaded of the dreadful attacks that are out there. There's a great website called Zerodium that pays for attacks. And the more desirable the attack is, the more they pay. And anything above $1 million, they will pay $1 million for a Windows attack, but it's got to be a remote code execution attack. So they're very desirable. It's very desirable to stop these. So we built this system. We built it on the RISC-V rocket core, extended the Chisel implementation of that particular core to do these capabilities. Austin and Tara Nash worked on that. It was a really fantastic piece of work. And it was deployed in FPGAs. And then we worked with DARPA. DARPA supported the work. We worked with them to do red teaming on this particular thing. We put free RTOS on it, and we put on top of it a database and put a web interface on the database. And then DARPA worked with a company called SYNAC that organized red teaming around these targets. And we were attacked for 3 months by 535 attackers, and we had 0 penetration. So it was a great success that this technology could stop that. So this is a really interesting new technology based on this idea of randomization with churn, where we re-randomize. And we're really sort of doubling down on this idea with great concern. And then also, Lauren, who was also one of the architects of the Morpheus architecture, she's my PhD student. She's also been involved in sort of generalizing this capability of encrypting key values in the program. And she's developed what we call privacy enhanced computation. The idea here is um, it's more than just encrypting and randomization as a way to make it hard to forge stuff. What we want to do is we want to build a system that can compute on data that it doesn't know what that data is, like homomorphic encryption. In fact, homomorphic encryption is really inspiration for this work. And so you've got some remote data owner that owns some data. They can encrypt that data under a secret key. They can share that secret key with the hardware, but they can't share it with the software. So you have to trust the hardware, but you don't have to trust the software. And not trusting the software, it's not as good as homomorphic encryption, which doesn't trust the hardware or the software. But not trusting the software, it's a beautiful thing, because it means all those attacks that that security researchers and security engineers at companies pull their hair out about all the time, they don't have to worry about those, because there's the software doesn't have access to that data. And this privacy enhanced CPU can compute directly on that data without a known key, without any key known to software. And it produces encrypted results. So imagine an add instruction. It takes two encrypted operands and it creates yet another encrypted operand. It's really cool technology. And you probably think, well, it used inside this core, it's basically decrypting with AES, two operands, and then doing a single op, and then encrypting the result and giving it back to memory. And so, at first blush, you might think, oh, wow, AES is 40 cycles to decrypt, 40 cycles to encrypt at ALU speeds. I mean, it's really expensive. But Lauren's actually figured out how to hide almost all of that latency. In fact, with 40 cycles of decrypt and encrypt on a one cycle ALU op, she's got that exposed latency down to about 20%, 1.2 cycles. Really impressive stuff. So now this is really an area that we're really focused on. And how this intersects with memory security is, well, you don't have to worry about so much in your memory because all your secrets are encrypted all the time. They're not decrypted in the registers. They're not decrypted in the caches. They're not decrypted in the DRAM. And so the security really comes down to, can you break my crypto? Can you break my crypto? Can you side channel my secure core? And so it's really about eliminating side channels and building efficient cryptography, which is really what we're all about anyway. So it's a really just sort of a finely honed version of that. And it's really exciting. I'll just give an example. One of the algorithms that Lauren's implemented, which is really exciting for us, is genome analysis. If you've ever used 23andMe, right? 23andMe, they sequence your genome and they tell you if you have relatives that were Neanderthals. And in the process, they've acquired your DNA and they sell it to drug companies to try and do drug discovery on it. Now, that may be okay, but they didn't get your permission to do that. And your DNA is special, right? Your DNA, your genome is you. There is no revoking your genome. Once it's gone, it's gone. Once the world has it, the world has it. So this idea that you could take a genomic sequence, encrypt it, and then tell me if I have relatives that are from the Neanderthal era without knowing what my entire genome was, is that's a very interesting and exciting thing. We can do it in homomorphic encryption. We can do it in what Lauren calls privacy enhanced computation. Key advantage of privacy enhanced computation, it's about 1 million times faster. So there's some advantages to putting this stuff into hardware as compared to homomorphic encryption. The downside is, with this work compared to homomorphic encryption, you got to trust your hardware. Well, we kind of do trust our hardware. I mean, I trust that AMD and Intel and ARM are not putting backdoors in my hardware. I extend that trust because I've never seen any counterexamples. So, but I don't trust that my software is backdoored, because we hear about that all the time. So, is it better? Is it worse? It's different. It's different. But this idea of privacy enhanced computation, be it homomorphic encryption, be it this style of encrypted CPU, very interesting. Lots of interesting stuff. Like, how do we import data from someone else without ever being able to see that data? That's exciting. How do we make this always encrypted computation fast? We don't want to pay 40 cycles on an ad on the front end and the back end. How do you write programs without being able to see the data? That's a really interesting problem. Basically, you can't make heuristics because you can't look at your underlying data, which is okay. It means your algorithms sometimes run about twice as long as they normally would because you can't look at the data and know that you're done. And then how do we safely analyze encrypted data? Lots of really interesting stuff. And how do you make this system resistant to those side channel attacks? And how do you make it resistant to analyzing the cryptography? Really interesting stuff. So that's my tutorial, my short course for IEDM. I hope you enjoyed it. It was a pleasure to give this to you. I hope you learned something. I hope you've got some interesting ideas to look more into. If you have any questions, drop me an email, austin@umich.edu. I'd be happy to talk more about any of this. If you've got nagging problems you're trying to solve and you want to know, better which direction to go in, I'm happy to talk to you about that. Please share this video series, this two-part series with your colleagues, and please stay secure. All the best. Take care.